Hello everyone, my name is Shreyas Mandem, and today I will be presenting my project SmartPrefetch, a prefetch based suppression system which me and my teammate Aditya made under the guidance of Dr. Anuradha ji. Now let's first begin with the memory wall. The CPU works at incredible speeds, but the RAM operates much slower, and thus the data isn't immediately available. Let's take an example of a restaurant. A chef cooks food really fast, but doesn't get the ingredients from the pantry that quickly. So the chef will have to wait for the ingredients to reach him. And this is why there's a cache storage, a memory bank right next to the CPU which stores the most accessed data. In restaurant terms, this acts as a mini fridge which stores the most used ingredients that the chef requires right next to him. So how does prefetching play a role in this? A prefetch helps fetch data into the cache even before the CPU asks for it. It does this using predicted access patterns, and in restaurant terms, the helper figures out which ingredients the chef uses the most and puts it in the mini fridge. But there's a catch. Prefetchers only work for predictive access patterns, like when an array goes from 0 to 10 or anything in order. But when there's irregular patterns, such as graph algorithms, space matrices, machine learning, or pointer heavy codes, a regular prefetcher fails as it cannot analyze the patterns due to its mixed nature. It's like the chef making a dish with a variety of ingredients, and the helper doesn't know what to add to the fridge next. This causes two issues: cache pollution, where the cache is stored with items that will never be accessed, and memory bandwidth waste, where the prefetcher is utilized for no use. And this is where Smart Prefetch comes into play. It first measures the track hit on every prefetch batch, and it then evaluates if its utility is above the threshold and suppresses or resumes the prefetching based on evidence. So this is how the prefetcher decides if it continues or not based on this algorithm. And these are the results which we'll see in the next hands-on demonstration of how Smart Prefetch works. Now, let's see a hands-on demonstration between the difference of a Smart Prefetch and conventional prefetcher based on the simulation that we made. These are the parameters where you can choose cache lines, stream length, suppression threshold, and window size. You can choose your speed here and the workload here. A sequential workload works equally well in both a conventional and smart prefetcher, whereas graph, sparse, and mixed workloads always work better with a smart prefetcher because this can analyze and basically suppress and resume itself to reduce memory bandwidth. So let's run it and see the difference between both of them. Yeah, so you can see both the prefetchers going through the memory access stream, and you can see that a conventional prefetcher goes through every single memory address and sees if it's a hit or a miss. Whereas Smart Prefetch first predicts its usefulness with a hit and miss ratio, and then suppresses itself if it doesn't think it's useful, and then later on resumes itself and then continues on until it thinks it's not useful again. So you can see the suppression events here, and the event log also shows it. And this miss rate graph also shows that how Smart Prefetcher always performs better than a conventional prefetcher by having lesser misses. So this event log basically shows like how the Smart Prefetcher works, where it suppressed itself and resumed itself. And after it's done going through the memory access stream, you can see how a conventional prefetcher has a higher miss rate than a smart prefetcher and always issues more prefetchers than a smart prefetcher. So basically, the smart prefetcher can do the same amount of thing with lesser prefetchers issued. So it basically saves memory bandwidth. And so this is our simulation, and you can also try it with the link in the description. Now, let's see how we can simulate smart prefetch using Python. So this entire code is basically a comparison of smart prefetch versus a conventional prefetcher, and it shows the amount of bandwidth saved by a smart prefetcher compared to a conventional prefetcher. So let's run the code now. Yeah, you can see the output here. So these are the kinds of workload: sequential array, graph, sparse, and mixed. And you can see in a sequential array, a conventional and smart prefetcher's miss rate is the same. You can see there's no improvement here because it has a predictable workload. But for graph, sparse, and mixed, you can see a smart prefetcher has a significantly lower miss rate. And this is the amount of improvement that it has. So, and this is the bandwidth saved. And you can also visualize this by the image that it generated. Yeah. So these graphs of each workload basically show how Smart Prefetcher performs significantly better than a conventional prefetcher. Like in a sequential array, when both are the same, there's no difference. Whereas in any other irregular workload, you can see that the smart prefetcher has a lower miss rate over time. Thank you.